Here's a solution to the quiz from last week. So in this problem, some people noted that you can solve this using the guess and check method, and I guess that was fair enough. I give you credit if you did that correctly. But let's talk about how to solve this problem using calculus. So the setup is you have this area, and there's a field, and there's some rocky mountains, and you want to get from point A to point B. And if you just try to take the shortest distance between point A and point B, which would be straight across the Rocky Mountains, then that distance would be, of course, the square root of 100 squared plus 75 squared. If you were taking this distance, and since you're running across rock, you would only be running at 2 meters per second. So if you check, this will take you greater than 60 seconds. So you don't want to do that. What you want to do is you want to run along here until you get to a certain point, and I'm going to call this distance right here x. And then you want to leave the field and run across the Rocky Mountains the remaining way. If you take a strategy like this, then you can figure out your minimal time to get to the house by minimizing the time function, which would be your time across the field plus your time across the mountains. And what we're going to do is we're going to take both of these, this time across the field and time across the mountains, and express them in terms of this quantity x. And then we'll use calculus to figure out which value of x would give us a minimum here, right? So to do that, we have to note that the time that takes us to cross the field is going to be the distance that we stay on the field divided by our rate, which is given in the problem as 4 meters per second, plus over here, for our time in the mountains, it would be, this would be the time that we would actually spend. This would be the actual distance we would spend in the mountains, right? The length of this segment. And we can figure out that using the Pythagorean theorem, right, as x squared plus 75 squared. So solving for dm here, we would get the square root of x squared plus 75 squared over 2. And then we can also go back over here and we can plug in df, because this would be df right here, right? So that's going to be 100 minus the total distance, x there, right? So this is our function to minimize here, basically, right? And this sort of stuff up here, figuring out how these distances are related to this variable x, those are the constraints in this particular problem. Okay. So once we've set up this expression, now we can use calculus by taking its derivative with respect to x and setting that equal to 0 and figuring out which distance x would give us the minimal time, right? So we're going to differentiate. And I noticed a lot of people trying to apply the quotient rule here, but you don't really need to do that. Just think of this as split up the 4 here, and you would just get 25 minus 1/4 x, whose derivative would just be negative 1/4. Now over here, you do need the chain rule. So we take the derivative of the inside, and then we multiply it by the derivative of the outside, which would be 1/2 square root of x squared plus 75 squared. And we set this equal to 0, we do some algebra, and we solve for x, and we end up getting that x is about 43 meters. Okay. So once we have this x, we want to do two things. We want to figure out what would be the time up here, right? So we want to plug this x back into here and figure out, is that a time in which we will actually reach the, will we beat the 60-second mark given in the problem? And second, we want to use this to figure out how long we should run on the field. Of course, that part's easy because we just subtract this from 100, right? So first of all, we take the 43, we plug it into time, right? And you end up getting something in the order of 57 seconds. So that's good. We'll make it. We won't be eaten by the zombie. And our optimal strategy, then, the distance should be 100 minus 43. So we should stay on the grass about 57 meters. Now, how do we know that this is a min and not a max? Well, we have a closed interval here, so we could plug in x is 0 and x is 100 into this function and check those. And in both cases, you get something that's larger than this. So it stands to reason that this is going to be the minimum over the interval.